Hello dear friends, welcome to a lecture on ring theory. In this lecture we shall study polynomial rings. So here first we shall form a set of polynomials, and for that purpose I have written here the meaning of a set of polynomials in a field, and then the equality of two polynomials is defined, and also we define what is addition and multiplication in polynomials, and its illustration is written with the help of example. Then we shall prove that this set of polynomials over a field forms a commutative ring with unit element. Now consider f be a field, or let f be a field, and it may be of real numbers or rational numbers, etc. The ring of polynomials in the indeterminate x. X is a variable here which is indeterminate, and we write this as f of x. Ring of polynomials. Here field is considered. Sometimes any ring may be considered, and in that case it is denoted by r of x. But here we have considered f as a field, and therefore we will denote it as f of x. And this ring f of x is the set of all symbols, that means polynomial, and we know usual algebraic polynomial is written in this form: a naught plus a1x plus a2x square plus so on an x power n. This is nth degree polynomial, and where n is any non-negative integer, this power of x is, or the coefficient n is non-negative integer, and the coefficients a0, a1, a2, an are all elements in the field. The coefficients are elements of field. So such a set we shall consider, set of all polynomials. We have studied earlier polynomials, usual polynomials, say 1 plus 2x minus x square. This is a polynomial of degree second. Here a0 is 1, a1 is 2, and a2 is minus 1, etc. So it may be of, in general, polynomial of nth degree, and that is written a0 plus a1x plus a2x square and so on an x power n. So such polynomial set is considered, and the coefficients are the elements of field. Now what we shall define is the equality of two polynomials, addition of two polynomials and multiplication of the polynomials here in these two definitions. First is consider p of x, a polynomial of degree m. We will define degree separately again, but we know it. P of x is written as a0 plus a1x up to am x power m, and q of x is b0 plus b1x and so on bn x power n. These are two polynomials in this set f of x. Then we say, or we define, these two are equal if and only if ai is equal to bi for all I greater than or equal to 0. Corresponding coefficients are equal. The ai is equal to bi means a0 is equal to b0, a1 is equal to b1, a2 is equal to b2, and so on. Am must be equal to bm, or bn must be equal to an, and that means a polynomial is equal to itself. All corresponding coefficients are equal, then and only then the polynomial will be equal. So that is the equality of polynomials. Now second, here we consider again p of x as above, and q of x is another polynomial. Both are in this set denoted by capital F of x. And then we define addition and multiplication are defined as, first is addition, p of x plus q of x, and that is written as, it is again a polynomial which is written in this form: c0 plus c1x plus, we write the x terms in ascending powers. So c0 is a constant, c0 plus c1x plus cpx power p. Any notation can be used for this suffixes and power. P is non-negative integer, where for each ci is equal to ai plus bi, means C naught will be equal to A naught plus B naught. C1 will be equal to A1 plus B1, and this is usual addition of polynomials that we already know. And if you want to add this Px plus Qx, we will consider example separately there. Then this will be A naught plus B naught plus A1 plus B1 times x, and so on. So that the addition is easy to understand. Now, but you see how the multiplication is defined. Px into Qx is equal to C naught plus C1x. We have used the same coefficients, but it should not be confused with addition, and this is multiplication, it is separately. C naught, here C is defined separately, and here C is defined differently. C naught plus C1x plus Ckx power k, where in multiplication Ct, the coefficients is expressed as Ct is equal to At b naught plus At minus 1 b1 plus At minus 2 b2, and so on, plus last term is A naught bt. And you see here the sum of suffixes of A and B is t plus 0, then t minus 1, t plus 0 is t, t minus 1 plus 1 is again t, and that means sum of suffixes of A and B is constant, that is t. So this is in this way the Ct coefficient in the product is formed, and it starts with At b naught, and then the suffix of A decreases by 1 and suffix of B increases by 1, and the last is A naught and B suffix is t. So in this way the product is defined. Actually it is again usual product of polynomials we have done earlier. And here how this addition and multiplication are defined. To understand this, I have written here the illustration for addition and multiplication by taking two polynomials. The first is P of x is a polynomial 3 plus x minus x square, and Qx is 1 minus x square plus x cube. These are the polynomials in this set f of x. And by the expression or by the definition of polynomials, we write the coefficients. Here P we have written A naught plus A1x etc., and therefore this is A naught. A naught is 3, this coefficient of x is A1 which is 1, coefficient of x square is A2 which is minus 1, and the further coefficients are 0. Here only 3 coefficients are there, A naught, A1 and A2. A3, A4 higher coefficients are absent, and therefore they may be denoted with 0. And similarly for Q of x, B naught is 1, B1 is minus 1, B2 is you observe here it is A naught, B naught is 1, and here the term x is absent. So therefore it must be taken with 0 coefficient, 1 plus 0 into x, and therefore B1 is 0 here, and this is the coefficient of x square, that is B2 which is minus 1, and this is the coefficient of B3, this is the coefficient of x3 which is B3 is 1, and higher coefficients B4 etc. are 0, but these terms are absent. Now how the addition is defined? Addition is simple. When we add these two, we add A naught plus B naught, that is 3 plus 1 which is 4, that is C naught. C1 will be A1 plus B1, A1 plus B1, 1 plus 0, that is 1. C2 will be A2 plus B2, minus 1 plus minus 1, that is minus 2 into x square. C3 is A3 plus B3, A3 is 0, B3 is 1, and therefore its C3 is 1 into x cube. This is addition of two polynomials, or we can add the similar power terms and get it easily. So this is usual. And now how the product is defined? See, Px into Qx is again written in the same form, C naught, but here the coefficients are defined differently. C naught plus C1x plus C2x square plus C3 x cube plus C4 x raised to 4 plus C5 x power 5, because in the addition the degree of the product becomes sum of degrees of this, that is 3 plus 2 5, and therefore this is a 5th degree polynomial. Product is a 5th degree polynomial, and where Ct as earlier in the definition of product is defined like this, A t b naught etc. Now how to calculate the coefficients here in the product? C naught, put t is equal to 0, and then this is only first term, only one term is there in this coefficient C naught. T 0 means A naught B naught is the first and the last term, and A naught is 3, B naught is 1, so therefore A naught B naught is 3. So it is actually 3 into 1, 3 into 1, and that is equal to 3. This term is 3. What about C1? C1 t is equal to 1, and therefore this is A1 B naught, A naught B1, and A1 is 1, you see A1 is 1, B naught is 1, so 1 into 1, A naught is 3 and B1 is 0, so this is 1 plus 0, that is 1. C2, it is A2 B naught. Start with this A2 and this as with the 0 suffix, 2 1, then 1 1, then 0 2, like this. Decrease the suffix of A, increase the suffix of B, and the sum must be always 2. Sum must be always here t of suffixes A and B. In that way we can write the coefficients, and this gives A2 B naught plus A1 B1 plus A naught B2, and we put the values of AI's and BI's, and we get C2 is equal to -4. You can verify this. Similarly, C3 is written A3 B naught, A2 B plus A2 B1 and so on, and putting these values we get this as C3 is equal to 2. C4 likewise, C4 is written as A4 B naught plus A3 B1 and so on, and after putting these values, see A4 is 0, so it is 0 and B naught is 1, like that the values. So only the existing coefficients are here, non-zero coefficients are considered, or up to degree 2 the coefficients are to be taken, and further coefficients are to be considered as 0 in both the polynomials, and then we can use that values. A4 is 0, B naught is 1, A3 is 0 again, A4, A3 are 0 here. The polynomial is of second degree only, and therefore there are 3 coefficients. And then A2, B2, putting these values, this we get C4 as 2, and similarly C5, A5 into B naught, A4 into B1 plus A3 into B2 and so on up to A naught B5. Put these values. Now here A4, A5, A4, A3. A5 is also 0, A4 is also 0, A3 is also 0. So first 3 terms are 0. And then A2, B3. B3 here is 1, A2 is -1 into 1, etc. And this value is -1. So thus we have calculated what are C0, C1, C2, etc. And therefore what will be this product? See, the product will now be Px into Qx. Is equal to C0. C0 is 3 plus C1. C1 we have 1 into x, that is x, plus C2, that is -4 into x square, and C3 is 2 plus 2 into x cube, and C4 is 2 into x raised to 4, and C5 is minus x into x power 5, and thus the product is formed according to this definition. So how the definition is to be used and how the coefficients are written, to understand or to illustrate this, we have taken these two examples. Addition is simple, and actually the product is also simple. In the usual way we can obtain the product, because see this or you see px into qx, px multiplied by qx is this is 3 plus x minus x square into 1 minus x square plus x cube. And we know how to multiply these two polynomials. If you consider the degree in increasing order, then the constant term is to be written first. See the constant, 3 into 1, that is 3. And therefore it will be 3, and then you see this is 3 into 1, that is constant only, and term of x, x into 1, that is plus x, and term of x square, there will be two terms of x square. So minus x square into 1, that is minus 1 into x square, and minus x square into 3, that is minus 3 into x square. Minus 1 minus 3 is minus 4 x square. So which are getting the same. X cube, x into x square, that is minus 1, and minus x square into, so only one term is the x cube we are getting, x into x square minus 1, x cube into 3, that is plus 3. So which is plus 2x cube, and power 4, you observe x into x cube, that is 1, and this is plus 1. So plus 2x raised to 4, and the fifth power, that is minus 1 x raised to 1. So which is the same. So directly also we can get in usual way the product of these two, and it comes the same, and according to this definition it is also the same. So we can verify, we have verified this actually the definition of multiplication by taking this particular example. Now we shall state and prove theorem that this set f of x forms a commutative ring with unit element, and we write it as a theorem. The ring of, then let F be a field, then the set of polynomials f of x forms a commutative ring with unit element. That we shall state as a theorem. So we shall state and prove the theorem, and f of x, I shall write theorem here. F of x, just we have considered set of polynomials over a field f. F of x means is a commutative ring it is a commutative ring with unit element. That is the theorem. And to prove this, it forms a ring, and then in addition it is commutative and it has unit element. So thus in all we have to prove the axioms of commutative ring with unit element, and that means f of x is abelian group under addition, and in addition to that it satisfies the certain properties for multiplication, that is multiplication is closed then it is associative and it is distributive, and in addition to that it has unit element. So all these axioms we shall have to verify, and we can prove like this. We shall consider 3 polynomials in this f of x. In the set f of x, let px, we denote the polynomials p, q and r belongs to f of x, and in particular we may write these polynomials like this, as in earlier case we have written p of x is a naught plus a1x plus so on up to am x raised to m, q of x as b naught plus b1x plus so on up to bn x raised to n, and r of x is equal to, here the coefficients may be instead of c we may write this as d naught plus d1x plus so on up to dl x raised to l, where ai, bi, di belongs to the field f. And now we shall prove the properties for addition, closure for addition. We shall prove that this f of x with addition and multiplication forms a commutative ring with unity. The meaning of this theorem, and the operations are addition and multiplication that we have just defined here, addition and multiplication. So closure for addition. Now take any 2 elements p and q, and then we have, or for p, q belongs to R fx. For px and qx belongs to f of x, we have p of x plus q of x as this, according to this p of x plus q of x, we have denoted this as c naught plus c1x plus c2x square and plus so on, and that in general is denoted by ckxk, where ci is equal to ai plus bi for all I greater than or equal to 0, and this is again a polynomial because ai, bi are elements in field, and therefore ci is also element in field, and therefore this belongs to f of x, and this belongs to f of x. Hence the closure property is satisfied since this belongs to f field, and therefore the closure property is satisfied. Now associative. So these are the properties which are easy to verify. Associative for addition. Second, and here we shall consider 3 polynomials as p, q, r, and this belongs to f of x. So we have p of x plus q of x plus r of x. This is, now we may see here this, if you write this as again in this form, addition form, c naught plus etc. See, we shall get the result as this is same as P of x plus Q of x plus R of x. Since the reason for this is simple, since what are the coefficients of P? A naught, that is AI, plus, and coefficients of Q are BI, and coefficients of R we have written as D, DI is equal to AI plus BI plus DI. As these are coefficients are elements of field, and in field the addition is associative. Therefore, as these are the elements of field, AI, BI, DI belongs to field, and therefore the associative property satisfies for addition of polynomials. Now next is identity for addition, and we can see zero polynomial, the polynomial whose all elements are 0 is identity for addition, or 0 element. The polynomial zero, which is written as 0 plus 0x plus 0x square, etc., whose every element is 0, is this is in f of x, and is identity for addition. Identity for addition or 0 element. Now additive inverse. The next property, we are verifying one by one properties for a ring, and then we shall verify it is also commutative and having unit element. Now what about the additive inverse? Negative of the polynomial is the additive inverse, and thus if we consider this polynomial as p, then negative of p will serve as the additive inverse of p of x. Additive inverse or inverse for addition. For px, p of x, p of x is this polynomial a naught plus a1x plus so on up to am x raised to m belongs to f of x. Negative of px is negative a naught, negative or minus a1x minus and so on minus am x raised to m. This also belongs to fx, is the additive inverse, because their sum is 0. P of x plus negative of p of x is 0, and therefore these are additive inverse. It is additive inverse of p of x, and now thus it forms a group. And now see one abelian group for addition. So commutative for plus, that we shall prove. Commutative for plus. Fifth property. Commutative for plus, and that is easy. See, we have p of x plus q of x is equal to q of x plus p of x, as ai plus bi is equal to bi plus ai. In field, the coefficients are the elements of field, and they are commutative with respect to addition. So therefore the commutative property holds for addition, and thus it forms abelian group with respect to addition. Now what remains are the properties for multiplication. Now next we shall consider as next property as further closure for multiplication. Closure for dot, this property we shall consider, and that means we shall have to prove that the product of two polynomials is again a polynomial in f of x, and for that purpose we can consider p of x into q of x. We have defined earlier the multiplication of polynomials, and that multiplication can be expressed as we have p of x into q of x, and that we have written as c naught etc. So this is the polynomial that we have written here, p into x, p of x into q of x we have written as a c naught etc., and that we can write as c naught plus c1x plus and so on up to say some ct x raised to t, where this ct is at b naught plus at minus 1 b1 and so on. We have defined it earlier, a naught bt. So this belongs to the set of polynomial because these are the elements of field, and this belongs to f. All these belongs to f. Therefore the multiplication is closed. So closure for multiplication that we have verified. Now next is associative for multiplication. And that property we know is taking three polynomials, their product is associative. So that can be considered as p, q are three polynomials, and we write their product as we have p of x into q of x into r of x is same as p of x into q of x, and then it is multiplied by r of x. So because the coefficients, their coefficients satisfies the associative law for multiplication. Since the reason for this may be written as since ai, bi, di belongs to f, and the coefficients are elements of field and they satisfy associative law for addition, and the product is product of these elements in f is associative. Now what further compulsory property for ring remaining is distributive law, that is multiplication is distributive over addition, and that there are two laws, right and left. Distributive laws that is px into bracket q of x plus r of x. This is equal to p of x into q of x plus p of x into r of x. That is one. And second is q of x, it is a left and right distributive law can be written as q of x plus r of x multiplied by p of x is equal to qx into px plus r of x into p of x. So this distributive laws also hold because the coefficients are again elements of field, and in a field the distributive law holds, that is multiplication is distributive over addition, holds in f of x. So thus this f of x is a ring. Now what remains to prove is it is commutative with in respect to multiplication operation, and it has unit element. Now commutative for multiplication, that we have to prove. So this is our ninth property. Next to this, commutative for multiplication, and that means this px into qx is equal to qx into px, as the product of coefficients in the field is commutative, as ai bi belongs to f, and the product in field is commutative. Now what remains is the unit element. So last property, unit element, and this element we can consider as usually denoted by 1, and we write this as 1 is equal to polynomial 1 So we have 1 is equal to 1 plus 0 into x plus 0 into x square plus 0 into x cube, and so on. This is a polynomial. 1 can be written in the form of polynomial in f of x, and this belongs to f of x, and this serves as the unit element, is the unit element. Since see, p of x into 1 is equal to p of x, or 1 into p of x, and that is p of x, and therefore this is the unit element, 1 is the unit element, and thus all the axioms of commutative ring with unit elements are verified for this set of polynomials with the addition and multiplication of polynomials, and thus this f of x is a commutative ring with unit element, and this is known as a polynomial ring. So thus in this lecture we have defined what is f of x, its addition operation and multiplication operation, and verified the axioms for commutative ring with unit element. I hope you understand this. Thank you for watching the lecture.